Okay. Recording in process. Hi guys, thanks for coming here today anyway. So what I'm trying to do here is just to expand people's knowledge. A lot of people have asked me to give them some guidelines on different parts of fire engineering. So I thought it'd be a good idea if I got something together, which I took back from my course notes in 2006, 2007. Now, I'm going to try and do it sort of 15, 20 minutes, no longer than half an hour each week, concentrating on just small parts, different subjects. Now, I might mention Australian standards and things, but I'm not going to point people in a direction to a particular part of an Australian standard because they change so much, and so does the building code, as you all know. So something like access and egress is part D of the building code. So if you need to know anything on access and egress, just go to part D. Okay. Things like fire extinguishers maintained with AS 1851, forgotten what part it is, but then you've got placement of fire extinguishers, AS2 treble 4, for example. Okay, same with emergency lighting. So one Australian standard leads into another, and you know how quickly those change. Okay, so all we need to know really is there's Australian standards, building codes, and Australian standards, and then of course all your own state regulations as well, which you've got to look at. So what we're going to talk about in this first session here is something we all need to know in fire engineering: how to combat fire, the three essential elements of a fire, the fire triangle or the tetrahedron, all the states of matter, fire points. Okay, a lot of people don't know about fire points. They're quite interesting. We're going to talk a bit about smouldering, flaming, and spontaneous combustion, and some facts on smoke of what can kill you, and how smoke is produced, and different types of materials, and the quantities produced, and the heat produced from those different quantities of different types of materials. And then lastly, we'll just finish off with the International Fire Engineering Guidelines, which defines the untenable conditions in a building, which fire engineers are trying to make buildings tenable for people to escape from without getting smoke inhalated or burnt to death. Also, on that, they're trying to make it safe for the firefighters to go in and fight the fire. You with me? Good. So 4 things we need to know: the easy ignition, i.e. how easy is that fuel going to burn? Things burn in different ways and different speeds. So petrol burns at around about 100 miles an hour and very quickly. You get a piece of metal, you've got to go up to thousands of degrees before it starts to burn. The rate of growth, so how fast is this fire going to grow? How much heat is produced from this fire? So different materials produce different amounts of heat. And the gas and the toxic gas production, which is produced from these different materials. So rubbers and plastics produce huge quantities of smoke, huge amounts of toxic gases in them. So we need to know all that stuff to be able to combat a fire in a building and to be able to keep people safe, to take that smoke away, take the heat away, simply putting it. So the 3 essential elements for fire to exist, you guys already know this. You've got fuel, which comes solid, liquid, and gas. Everything in life goes from solid, liquid to gas, and it's only the gas which burns. The heat, which is a chemical reaction, or electrical energy or nuclear reaction. Oxygen in the air is about 19%, so you need the right amount of oxygen, fuel and heat for a fire to burn. Almost anything will burn in life, apart from the bottom side of a space shuttle and water. So the 3 states of matter is solid, which comes in paper, wood and fabrics; liquid, which is petrol, kero, meths, paints, all that type of stuff; and then you've got gases like your LPGs, acetylene, all that lot. And as I said, everything goes through life from solid to liquid to gas, and it's only the gas that burns. So a piece of paper, literally, when you burn it, it literally melts and the gas then ignites. A piece of wood, you heat it up to the right temperature, and it will start to smolder, start to smoke, and then it will go into a flaming fire stage, and that is the gases produced off this piece of wood, which is burning the gases which are produced off the wood. They all have very different flash points, fire points, and auto ignition temperatures, which I'll go through in a minute or two with you. So the combustion triangle, as I said, you've got heat, fuel, and oxygen, and all those together produce a fire. If you take one of those away, if you take the fuel away, you're not going to have a fire. If you don't have the right amount of oxygen, you're not going to have a fire. If you're not going to have the right temperature of heat, you're not going to have a fire. Okay, so a flash point is the lowest temperature a liquid will ignite where adequate vapors have been produced. And if you've had a look at the Chinese on their woks, they got the woks going and they tip it towards a fire and it flashes momentarily and then goes out. Well, they know the oil they're using is hot enough and it's not too hot. It's not going to burn the food, not going to burn the spices, whatever they put in it. They put it in and cook it. If it continues to burn, they'll take it to one side and leave it because they know then it's too hot and it's going to burn the food. They don't know what they're doing. They just know in their cooking training that if it carries on burning, your fat's too hot. Now, all fats and oils burn at very different temperatures, and that, again, I'll explain in a minute. A fire point, when it's gone past its flash point, which is normally around about 10% higher than its fire point, is normally 10% higher than its flash point. Okay, so it's not, there's not a very large range there. And what I do, if this, as I said earlier, the Chinese, they tip it, the wok to one side. If it carries on burning, it means it's gone to its fire point. If you put a match, light a match and put it into oil and it carries on burning, it's its fire point. The auto ignition temperature, which is the dangerous part of it, very dangerous part, is when a substance will grow with burn with no external heat source. So think about your cooking oils. You've got your cooking oils on the stove and it catches fire. It's got to its auto ignition temperature. You all with me? So you've got flash point, fire point, auto ignition temperatures. And this is some examples of flash point, fire points, and auto ignition temperatures for different types of materials we use today, different types of fuels around. So petrol, its flash point is around about minus 40 degrees C. Fire point is minus 38 degrees C. Auto ignition 260 degrees C. So I wouldn't advise you do this at home, but if you put some petrol into a pot and heated it on your stove, you'd know when it's got to 260 degrees because it catch fire with no external heat source. So minus 40 degrees C, so that makes petrol very volatile. So if you can imagine on a normal average day in Australia, 25, 30 degrees, that's 70 degrees above its flash point. And it's going to catch fire if you put an external heat source in there. Petrol, by the way, is in its solid state at around about minus 50 to 60 degrees C. So from its solid state to its flash point where it's melting is not very high at all. Kerosene, you look at that as plus 38 degrees C for its flash point, and its frozen solid state is around about 60 degrees C. Fire point around about 40 degrees C. Auto ignition, interestingly, around about 210 degrees C, which is 50 degrees lower than petrol. If you look at then cooking oils, you know, you cook your chips and whatever at around about 170 to 180 degrees C. That's not far off its flash point. And then its fire point's 270. Take it anywhere between 400, in fact, up to 1,000 degrees C, and you've got an auto ignition temperature. And those temperatures there are so high, what happens when people put water into a deep fat fryer, it basically turns into a mini volcano. Water expanding, if you put an average cup in there, it turns into about 400 litres of steam, which quickly, rapidly expands and blows that oil into the air. And if you think about a fuel triangle, fuel, heat, oxygen, you've got a fireball in your kitchen. So very, very dangerous. You all get that, guys, yeah? Yep. Good. So a smouldering, this is their where you think about things as we go through this in the next few weeks, think about smouldering, flaming, and spontaneous combustion. So smouldering means to burn slowly but no flame, and it produces copious amounts of smoke, large particles of smoke, or more than 1 micron in diameter. A flaming fire produces is a lot hotter, and the smoke particles are a lot smaller, because all smoke is unburnt products of combustion. Okay, so the more smoke you get, that's more products of combustion. So smoke on this ceiling layer is fuel ready to burn if it gets to the right temperature. Okay, a lot of smouldering fires, you know, in your house you have, and in office blocks and what have you, you have fire retardants. The idea of fire retardants is to slow that burning process down so it gets it smouldering, and the smouldering combustion then produces huge quantities of smoke, which then interfere with your smoke detectors and give you an early warning. Spontaneous combustion, well, that happens when you've got organic matter and you get the right amount of air and the right temperature, and it will just explode momentarily without you even knowing about it. Apparently, these people, they reckon, have died through spontaneous combustion. They found bodies in chairs when they'd been sitting there eating a cheese sandwich, and they spontaneously combusted. Apparently, started reading some articles. We used to be a bit anal about it in the Air Force. We used to go and empty our bins in the hangars at least 2 or 3 times a day because of oily rags and that, and they were just so frightened of this spontaneous combustion. Right, so flashover and backdraft. You've all heard over flashover and backdraft. So flashover occurs normally a fuel control fire, which means there's an excess of air. And what happens is the fire's burning and you've got air coming in and you've got loads of smoke being produced at the ceiling level. It gets to around about 600 degrees C, and that smoke will burn it. A radiant heat around about 20 kilowatts per meter squared down onto everything in that room, and it will just all ignite. You've got to bear in mind a fire doubles intensity every 30 seconds. I'll show you about that in a minute or two. So backdraft is when it's a ventilation control fire, i.e. the door's shut, you can't get ventilation in there, and you've got a fire which used up all its oxygen, and the fire dies down, and it's producing huge quantities of smoke, and it's very hot. So it could be at the ceiling layer of around about 600 degrees C, missing that side of a triangle, oxygen. If a door opens, rush of oxygen goes in, that smoke ignites, fires out the door, and then it turns into a flashover fire. So, things which affect smoke production. You've got the combustion process, obviously flaming or smouldering, the moisture content, and normally in wood, where you get a lot of steam produced. That looks like it's a lot of smoke. The temperature and oxygen levels, the size and shape of the fire, and where it's positioned as well, and what type of fuel is burning. So if you have a fire against the wall in your house and it catches fire, you basically cut down half the surface area where oxygen can get in and burn that fire. But what happens is it's trying to draw that oxygen in, and your flame is actually about 1.5 times higher than they would normally be if that fire was in the middle of the floor. The quantity and type of fuel burning, the movement of gases as the flume draws air in, and the presence of fire retardants as well. And just some facts here. I'm not going to read that up, just left it to you. It's about 50 to 80% of people die through smoke inhalation. They've got carbon monoxide poisoning normally, and hydrogen cyanide. And I put it like this: if you're going to collapse through smoke inhalation in a fire, at least you're not going to feel yourself burning to death. So the International Fire Engineering Guidelines, their definition of untenable conditions is the height of the smoke level. It's worked out through the height of the smoke layer, the toxicity of the smoke, the temperature of the smoke, the radiant heat and the direct contact. So untenable conditions occur when the smoke layer is greater than 2.1 meters above the floor, and the temperature is greater than 200 degrees C, and a radiant heat at 2.5 kilowatts. So if you think about what I said earlier, it doubles intensity every 30 seconds approximately. So every 30 seconds, then it's going to go to 5 kilowatts after 30 seconds. 30 seconds after that, 10. 30 seconds after that, 20 kilowatts per meter squared, which is when flashover occurs. So you've got about a minute and a half on an average fire. Or when the smoke layer is lower than 2.1 meters at floor level, and it's more than 60 to 100 degrees C. So fire engineers, you've got to design things to keep that smoke layer above 2.1 meters, keep the temperature down so people can walk underneath that smoke and into an emergency exit behind a fire door or firewall or another compartment, which we'll go into another day. If you just remember that there's untenable conditions, and these are what we're trying to engineer buildings to meet, to keep people safe, not just people evacuating, but obviously as well for firefighters. Is there any questions, guys, so far? No? Good, I'm doing all right time here. I hope we can hear this. It's just a... Can you hear that?
Start a fire on a chair, and the heat given off decomposes the foam or fabric of the chair faster than it can burn. The smoke, full of fuel, rises to the ceiling. As the smoke gets hotter, the three sides of the triangle, fuel, oxygen, and now heat, come together, and the smoke, finally reaching its flash point, ignites. This is what some call a rollover or lean flashover. As the fire now runs across the ceiling, it radiates heat downwards. This heat decomposes everything combustible. If there's a source of oxygen from an open door, or if a window breaks, then the whole room will flash over, everything bursting into flame. But if the room is sealed, double glazed and well insulated, then there's no new source of oxygen available, and the fire, missing a side of the triangle, drops back. Rich with fuel and heat, the smoke sits there like a caged animal, waiting for someone to open the door or break a window and feed it. This is what firefighters call a backdraft.
So I put that on because that explains it quite well, and you can see it. It's always good for visual. So what I've done, this is such a huge subject, and you can go on for hours on it, and it can get very complex as well when you go into mathematics of it all and that, but we're not going to go into that. But what I've got some YouTube links there for you, different things you can watch if you're interested in going further and having a look at what other knowledge you can get. Okay, is there any questions, guys? No. Next week, then, we're going to do the birth of the NCC, which is the BCA, the significant parts of the NCC concerned with fire safety, passive and active fire systems. And then we're going through I'm going to talk about fire doors and firewalls, which I consider is probably the most important part of the building, and there's a lot to them. And I'm going to talk about fire resistance levels as well.